All right, continuing and picking up where we left off in the last video. We've shown that if V1 and V2 are vector spaces, subspaces of Rn, our setting, then V1 plus V2 is also a vector space. That is the collection of all sums of a vector from this vector space plus a vector from that vector space. All right, we're going to look at a special example of that type of vector space sum called a direct sum. If V1 and V2 vector spaces, subspaces of Rn, are essentially disjoint vector spaces, that is, if they only share the zero vector in common, then the vector space V1 plus V2 is called the direct sum of V1 and V2 and is denoted with this little plus sign in a circle. All right, so the condition on this direct sum stuff is one almost of disjointness. These two vector spaces are as disjoint as they could be and still be subspaces of Rn. Of course, every vector space has a zero vector, and that's the only thing that they share. Theorem 2.1.4 says, if V1 and V2 are essentially disjoint, then every element of the direct sum, V1 and plus V2, can be written as V1 plus V2 lowercase vectors, where lowercase vectors V1 and V2 are from the obvious place, in a unique way. So the uniqueness claim is the claim. Okay, so let's look at a proof of that. So essentially disjoint, direct sum, unique representations. All right. Well, let V1 and V2 be essentially disjoint. That is, their intersection consists only of the zero vector. And technical difficulties. And suppose vector V is an element of the direct sum, V1 and V2. Then, being in just the sum of V1 and V2, we know vector V is of the form, say, V1 plus V2. Can also be written, say, in the form V1 prime plus V2 prime, where V1 and V1 prime are vectors from vector space V1, and V2 and V2 prime are vectors from vector space V2. All right, so essentially assume there's two different representations, and we're going to show that they are the same. Okay. Well, let's take this little formula here, get the V1s and V1 prime on one side, V2, V2 prime on the other side. So just move some things around. All right. On the left-hand side, we've got V1 minus V1 prime. V1 and V1 prime are both in vector space V sub 1. So their difference is also in vector space V sub 1. Similarly, V2 prime minus V2 must be a vector in V sub 2, being a vector space of n vectors is being closed under vector addition and scalar multiplication. It's exactly what we have here. Closure under linear combinations, if you like. All right. So these two vectors are equal. And then we must have these two vectors lying both in V1 intersect V2. But the only thing in V1 intersect V2 is the zero vector, All right, so it must be that V1 minus V1 prime is a zero vector. V2 minus V2 prime is the zero vector. That is V1, V1 prime, V2, V2 prime, those are equal. And the representation is unique. If you write vector V as a linear combination, as a sum of an element of V1 and an element of V2, then that choice of vectors V sub 1 and V sub 2 is unique. Totally based on the essential disjointness. You can see that right here where we drew the conclusion that the only thing in the intersection is the zero vector. To the notes. Okay. I'm going to define some kind of geometric things here. So we're not going to deal with this a great deal, but let's go ahead and get the definitions out there. A set of n vectors that contains all positive scalar multiples of any vector in the set and contains a zero vector is called a cone. Okay, so we have some kind of closure. It's a closure under only scalar multiplication, and then only when the scalars are positive. So a cone is a collection set of n vectors that satisfies closure in this sense. Oh, and it includes the zero vector because they said it does. A set of vectors, C, is called a convex cone if any two vectors v1 and v2 in that set C, the linear combination AV1 plus BV2 is also in that collection of vectors C, but we've got the restriction that A and B are non-negative. So it isn't closure under linear combinations, it's closure under linear combinations when the scalars you use are non-negative. Some examples, and we'll look at a picture. In R2, take C1, this will be a cone, to be all vectors of the form x comma 0 or 0 comma y, where x and y are each 0, union with the zero vector. Had to contain the zero vector. They said it contains the zero vector up here. This is a cone. What we've got here, we'll look at a picture, is all vectors lying along the x-axis, where the first component is positive, and vectors lying along the y-axis, where the second component is positive, along with 0. So here we have it. Let me make it a little bit larger. On the left, color-coded, so we get the zero vector. Here, big caveat, representing all these vectors in a picture where they're drawn in standard position. So actually what we're plotting is the points that lie on the head of a vector in this cone C sub 1 when that vector's been placed in standard position. Can't make a big enough deal out of this standard position thing. None of these pictures related to vectors make any sense unless you put them vectors in standard position. So this consists of vectors, say, in standard position, so with their tail at the origin, and their head lying this point, any point along the x-axis. It's color-coded in red. Similarly, tail at the origin and head at any point along the y-axis. Sure enough, if I'll take any one of the vectors in this C sub 1 set, if you'll multiply it by scalar, positive scalar, or non-negative scalar, you'll get simply a multiple of that in the same direction if you describe vectors like that. So you get another vector in set C sub 1. It is indeed a cone. Not a convex cone. We say that, yeah, not a convex cone. If I take the vector 1 comma 0 and the vector 0 comma 1, add them together, which you can do in a convex cone, would give us the vector 1, 1. Something out here in the first quadrant, standard position caveat being part of the rules. But that's not in C sub 1. So we don't have closure under linear combinations where we use positive scalars. Set C sub 2, we just saw a picture of actually. All vectors, remember the kind of unusual notation, new notation, I guess I should say. All vectors v in R2 such that vector v is greater than 0. Okay, that means all the components of the vector are greater than 0. So the first and second components are greater than 0, along with the 0 vector. Okay. So the claim is this is a convex cone. All right, so if we were to take any vector, taking vectors, the 0 vector, standard position, represented with a point at the origin, along with vectors that lie in the open first quadrant, So we chose those components to be positive, not greater than or equal to 0. So we get the open first quadrant. Certainly, if I multiply any of these vectors by a positive scalar, we get another vector in this red set, C sub 2. It is a cone. Not only that, but if you take a linear combination of any two vectors in this using non-negative scalars for coefficients, you'll get another vector in here. It's really just an artifact of the parallelogram law of addition. By taking positive multiples of the vectors, we're simply taking a vector, multiply it by a positive scalar. You're either stretching or shrinking it, but it keeps its, in a sense, its same direction instead of reversing direction like negative scalars would do. So think parallelogram law of addition, and that's the reason you get the closure here. In fact, we can go a little further. This picture on the right. A single cone versus a double cone, like you might encounter when you deal with conic sections in pre-calculus or calculus 2, I think conic sections come up. A single cone with its vertex at the origin in Rn is a cone in the sense defined here. Actually, it's a convex cone in the sense defined here. If we'll take any vectors in this cone, if you'll take a linear combination of the two, then you'll get another vector in this cone, implying, of course, that this carries on infinitely far, but trying to give it some perspective with little boxes and so forth, with the little dotted lines. But these are the reason they use the term cone. If I'll add together any two vectors in this yellow region in R3, then linear combinations using non-negative coefficients will give you other vectors in there. Why is that? That's parallelogram law yet again. Okay. We haven't defined basis yet. We're going to define basis for vector space. We're going to define basis for these cone things as well. Let G be a subset of a vector space V of n vectors, so a subspace of Rn. If each vector in V is some linear combination of the elements of G, then G is a spanning set or a generating set of V. We'll probably most commonly use the term spanning set. Generating sets, maybe a little bit more common in a setting of eigenspaces, or maybe when you're doing applications in the vectors or functions. We'll probably mostly use the term spanning set though. The set of all linear combinations of elements of G is the span of that set of vectors, denoted as PAN of G. If the spanning set G of V, the whole vector space, is linearly independent, then it's called a basis. So what's a basis? A linearly independent spanning set. That should ring a bell from your previous experience. Depending on your linear algebra experience, in the book they used, that's maybe the definition, excuse me, the definition of basis. Basis is a linearly independent spanning set. The book I love for sophomore linear algebra goes, it's something involving unique representations. That's fine. I say, whatever, you be thinking like this. Think that a basis is a linearly independent spanning set, because that is true whether you had a different initial definition of basis or not. Bases are linearly independent spanning sets. You want to think spanning set, there's enough vectors to write everything in vector space V as a linear combination of those basis vectors, spanning. Linearly independent, there's not any extra ones. So it's, in a sense, it's an efficient spanning set. Efficient in the sense of linearly independence. It's minimal, a minimal spanning set. Theorem 2.1.5 says, if we have a basis, say V1 through V sub k for vector space V, then each element of V can be uniquely represented as a linear combination of the basis vectors. Actually, the linear algebra book I like takes this as a definition of a basis. Here it's just a result of the definition, and let's look at that. This is actually very much a sophomore linear algebra type proof. Be kind of similar to the previous one. You're trying to show uniqueness, we'll assume there's two. Okay. Well, suppose vector x can be written as the linear combination b1 through b sub k as coefficients on this basis, and can also be written as c sub 1 through c sub k, linear combination of these basis vectors. Well, very similar to what we did in the direct sum theorem we saw previously. If we'll take the difference, x minus x, that'd have to be the zero vector. Let's take one representation for x and the other representation for x in that difference. Use your properties of vector addition, scalar multiplication, distribution, all that stuff. And we can collect together the v1. It has a b1 minus c1 coefficient. Vector v2 has a b2 minus c2 coefficient, and so forth. Hey, but here we've got a linear combination of v1 through v sub k set equal to the zero vector. But what's a basis? A linearly independent spanning set. Well, if these are linearly independent and we've got a linear combination of them set equal to the zero vector, then each of those coefficients must be the zero scalar. That is b1 minus c1, b2 minus c2, and so forth. They must all be the zero scalar. Or in other words, b1 equals c1, b2 equals c2, and so forth. So that representation for vector x was, in fact, it's unique. The coefficients you use are determined by the vector x itself. Exactly the kind of proof you might show in sophomore linear algebra, in fact. And a good one because it's an easy one. If we look at the direct sum of vector spaces again, remember they had to be essentially disjoint. If B1 is a basis for vector space V1 and B2 is a basis for vector space B2, where V1 and V2 are essentially disjoint, then the union, B1 union B2, the union of those bases, it's claimed as a basis for the direct sum. All right, why is that? Basis is a linearly independent spanning set. Well, B1 spans vector space B1, B2 spans vector space V2 because these were bases. Also, we've got linear independence within the B1s and within the B2s. So let's see, what's an element of the direct sum of vector space V1 and vector space V2? That's an element of V1 plus an element of V2. Okay, well, I got no problem with the spanning because that element of V1 is a linear combination of these vectors and basis B sub 1. That element of V sub 2 is a linear combination of these vectors. So anything in the direct sum certainly can be written as a linear combination of elements of B1 union B2. There's the spanning part. Hey, what's up with the linear independence part? How about we take the zero vector? The zero vector can be written as a linear combination of the B1s and a linear combination of the B2s. We know that the B1s are linearly independent. The B2s are linearly independent, leading us, were we to write the zero vector in terms of B1s only, to conclude coefficients must be 0. B sub 2 conclude coefficients must be 0 there as well, and leading us to a conclusion of linear independence of B1 union B2. All right, how about a little bit more stuff on this cones and another little geometric thing, an idea of a polyhedron. Set of vectors, V sub I, countable collection, not necessarily finite, such that any vector V in a cone C, there exist scalars A sub I, greater than or equal to 0, non-zero scalars, say for I equals 1 through K, such that V is a sum from 1 to K of A sub I, B sub I. And if for scalars B sub I non-negative, we have the sum of those same vectors equal to 0, implying that the B sub i's all must be 0. Then this set of vectors is called a spanning set or generating set for the cone. All right, now we got a little odd situation here where this spanning set itself could be infinite, yet we only took finite sums. So it's a spanning set, but we wrote every vector as a finite sum of these things. Yeah, we could only take finite sums. Well, you did series in calculus 2 and in loads of your analysis classes. Well, why don't we do series here then? What's missing? What is a series? Series is a limit, ain't it? A series is the limit of a sequence, the sequence of partial sums. Here's our problem. Can we take limits? You know how to measure distance? Well, not yet, not in what we've gone through. And we'll stay away from that, it turns out, because we're in finite dimensions. If we were in infinite dimensions, this would be a much more involved story. I think a more interesting story. Also, a story not for theory of matrices, a story more for analysis, probably functional analysis. We've got a class on the books on functional analysis where we'll talk about infinite dimensional vector spaces. But here's a story. When you do linear algebra stuff, it's finite linear combinations. You want to do infinite linear combinations, you're probably stepping out of the realm of traditional linear algebra. You're stepping into the realm of functional analysis. You're going, in a sense, from the finite to the infinite. And what do you worry about then? Well, divergence. So divergence is not an issue for us because we're only taking finite sums. When we say linear combination, we mean finite linear combination. That's just the setting where we are. So even though we started with an infinite set of vectors potentially, we're requiring that every vector v be a linear combination, a finite linear combination of those vectors. And the second condition is not exactly a linear independence, but something kind of analogous to a linear independence. We're requiring that when we get the zero vector as a linear combination of these v sub i's, that we must have used b sub i's, coefficients of 0. The b sub i's all being non-negative. If that condition were dropped, it'd be regular old just linear independence. But it's something slightly different here in this setting of cones. So that's a spanning set of a cone. If a spanning set of a cone has a finite number of elements, then the cone's called a polyhedron, and we'll draw a picture of that shortly. A spanning cone of a cone consisting of a minimum number of vectors, so they're using this minimum idea among all the spanning sets, is called a basis set for the cone. So there's a definition for basis of a cone. I think we'll use that, probably not a whole lot. But let's draw a picture of some of these things. The C1 and C2, the red cones we had upstairs. C1 was the positive x-axis, the positive y-axis, and the origin. That cone wasn't a convex cone. C2 was the origin along with the open first quadrant, saying quadrant and point, an origin, muddling the distinction between vectors and points. There's a distinction between vectors and points. Either that or I throw at you a whole bunch of stuff about standard position. Whenever we draw pictures, they come with a lot of caveats when I draw pictures in R2. So I need to be careful about distinguishing between points and vectors, probably more so than I am. Both of these have a basis of I and j. This satisfies the conditions as given up here in terms of a basis. Of course, these under ordinary circumstances, these are a basis of R2. But we're talking about this constraint. The real constraint is making the coefficients we use be non-negative. And so we get cone type stuff there, this deal with a polyhedron. Here's an example created by me in PowerPoint. So just sketched out. I didn't use any sophisticated software to make most of these images I use. Here we are in 3 dimensions, x, y, z, with 3 vectors, a green one, a blue one, and a red one. I get the little dotted line, little box type things to give you some idea of perspective in 3 dimensions. And if we take a linear combination of the 3 of these, then we're using non-negative coefficients, then we're going to get something that lies in this yellow wedge-shaped thingy here. So this polyhedron in some sense is related to 3. If I had a 4th vector, we might pick up a thing somewhere out here, and then when we took a cross section, we get some kind of quadrilateral. But these 3 vectors here determine sort of the edges of this polyhedron. It's got, well, the thing I've drawn here has got 4 sides to it. It's got 3, maybe you should call them faces. It's got 4 faces. Of course, this outer face or upper face is intended to project onward and outward. Right? It doesn't, the linear combinations don't end here, so we can stretch this thing out. And arguably it only has 3 faces. The 4th face is pushed to infinity, which is verbiage I hate, but that's kind of the idea. And if we had a 4th vector, then we'd see 4 faces back here and a cross section that's a quadrilateral, which is pushed to infinity as well. So that's the reason they're called polyhedra. They have this geometric interpretation as given here when you have a finite number of vectors in that spanning set. Okay, let's shift gears a little bit. Some really more familiar turf here. 2n vectors, x and y from Rn. Let's define an inner product. So let x have components x1 through x sub n, let y have components y1 through y sub n. Then the inner product, commonly denoted with these angled brackets, Langle and wrangle in LaTeX, L-A-N-G-L-E backslash R-A-N-G-L-E, Langle and wrangle, are the LaTeX commands to generate these. They're not simply less than and greater than symbols. It's a different font. But we're indicating inner products like this. You did a lot of inner product stuff in sophomore linear algebra, then you've seen this before. Even these symbols, also called scalar product or dot product. And if you only did a little bit of this in linear algebra, you did this because you did things in Rn, and we're in Rn with all our computations. So inner product of x and y, we'll use the more sophisticated graduate school terminology. Inner product is simply the sum of the product of corresponding components, x1, y1 plus x2, y2 plus x3, y3, and so forth. A vector space with an inner product is called an inner product space. So what we're going to do here is largely stuff you've seen before in sophomore linear algebra because we're dealing only with vectors in Rn. So we're only dealing with vector spaces, which are either Rn itself or subspaces of Rn for some n, like you do in sophomore linear algebra. This gets a little more interesting if you let me go to infinite dimensions. And we looked at infinite dimensional inner product spaces. Lots of applied math is done in infinite dimensional inner product spaces. If you've seen Fourier coefficients, those Fourier series are actually, they're actually, I want to call them linear combinations, except they're infinite, they're series. But in a sense, they're linear combinations in an infinite dimensional vector space. And those Fourier coefficients are determined by some projections based on a certain inner product. So even in the infinite dimensional setting, loads of applications of this stuff. Some properties of inner products. This is probably out of my sophomore linear algebra stuff, just a changing of notation. If x, y, and z are vectors in Rn and a is a scalar, then for non-zero vector x, the inner product of x with itself is greater than 0. The inner product of the 0 vector with any vector x equals the inner product of that vector x with a 0 vector equals the inner product of the 0 vector with itself equals a 0 scalar. My apologies, for the notation. That's a scalar, right? Right. Dot products, inner products are scalars. Real scalars for us we're taking a dot product or an inner product here of two vectors. So this must be the zero vector. This is a zero vector, and this is a zero scalar. Is that clear from context? It's implied by the context, at least. We've got commutativity. The inner product of x and y equals the inner product of y and x. Were we to use complex scalars, these would largely carry over. This is going to get a little more complicated here. The way we would define an inner product if we use complex scalars involves some conjugation, conjugates of complex numbers, and there would be an implication on what happens when you reverse the orders there. But everything for us in this class is real. So we got a commutativity of inner products. Scalars can go into the first entry as given, scalar A times the inner product of x and y. Does that make sense? Yeah, A is a scalar, and the inner product's a scalar as well. This is a product of two real numbers. Can also be computed by putting that scalar A as a coefficient of the first vector, and I bet you could probably put it as a coefficient on the second vector as well and establish that using some of the commutativity properties up here. And thirdly, we get a relation of vector addition to addition of inner products. We get like a linearity here in the first entry. It says the inner product of vector x plus vector y with vector z. There's the inner product of vector x with vector z plus the inner product of vector y with vector z. The oddball title for it, but notice the plus sign is very different. On this side of the equation, that plus sign indicates vector addition. On the right-hand side, plus sign represents addition of real numbers. So in very different settings, same symbol, unfortunately. Ooh, I bet that's true if we had the addition in the second component as well. So you can bring scalars in and out of inner products, first component or second component, it turns out. And you've got the fact that you can break up inner products over vector addition in the first component and in the second component as well. Let's run through a proof of part 3, total piece of cake. This proof, in fact, is probably from sophomore linear algebra. Usual thing, we'll take the question here in terms of vectors and turn it into a question in terms of real numbers. So take these vectors x and y, write them in terms of their components. Then let's take A times the inner product. All right, A times, substitute in for x and y, those expressions in terms of components. That allows you to compute, by definition, the inner product of x and y. We can distribute this A on each of these. Distribution, right, it's just numbers. A is a number, x1, y1, all these things are just numbers, so we're in the realm of numbers. So we do the distribution. Let's associate the A's with the X's, and let's recognize this particular sum as itself an inner product of the vector with components ax1, ax2 to ax sub n, inner product of that vector with a vector with components y1, y2 to y sub n. So we can write this like this, take it and use your notation to replace the x's, the component notation with x's and the y's, the xy notation we had. Here it is initially. Bring that scalar out front first, and that'll give us ax inner product with y. So super straightforward computation establishes that. Yeah, super straightforward computation would establish any of these. Okay. And as mentioned, we stated these claims up here in the theorem in terms of behavior of scalars interacting with the first component, and this vector addition thing as applied inside the first component of the inner product. Yeah, it works in the second component as well. So we can combine all those observations to say, hey, if we had a linear combination in the first component, inner product with vector z, we could get what you might want to call a linear combination of inner products. So there's a linearity behavior of inner products in both the first component and the second component. We can break these inner products up over the first component or over the second component. Okay. With inner products on the menu, you know norms of vectors can't be far behind. And when we deal with the norms of vectors, the big thing to prove will be the triangle inequality. And when proving the triangle inequality, you need Schwarz's inequality. This offer valid in finite dimensions, infinite dimensions, physics classes, wherever you need to prove a triangle inequality in a vector space setting, you're going to need a Schwarz inequality. Schwarz's inequality says, this is the exact same thing it says in sophomore linear algebra. Take vectors x and y in Rn. The absolute value of the inner product of x and y is less than or equal to the square root of the inner product of x with itself times the square root of the inner product of y with itself. Well, maybe in sophomore linear algebra, you use dots and dot product notation. And this thing over here, you might have expressed in terms of norms. And you had a product of the norm of x times the norm of y, which we will as soon as we have that particular definition of a norm or a norm notation. Okay, let's go through the proof of that. Proof we have is fairly straightforward. It's a little, I don't know, exotic, I guess. So let x and y be vectors in Rn. We're going to make this claim here. Okay, we'll prove this from scratch. You might think, well, let's take x and y and write them in terms of components. So we're going to go at it in a slightly different way and use properties that we know of inner products. Okay, let t be a scalar. So we're picking this scalar out of nowhere. And we're going to consider the inner product of tx plus y with itself. We just saw upstairs, part 1 of theorem 2.1.6. The inner product of a vector with itself is greater than or equal to 0. In fact, the only time it equals 0 is when one of these constituents is 0. But inner product of a vector with itself is non-negative. Think how they're computed. In Rn, you'd take the inner product of x with itself. You'd take x1 times x1 plus x2 times x2. You'd sum the squares of the components. Of course, that'll be non-negative. So there's a way to remember it. All right, so we're looking at this for some reason. Like I said, this is kind of an exotic proof. Let's see, we've got linearity in the first entry. So we can take this tx plus y, bring the t outside, break things up over the plus sign to produce this sum here. This is based on the linearity observed just a few seconds ago here using this plus sign and this scalar multiplication. All right, next, we can use linearity in the second term to break this up into two pieces and to break this up into two pieces. The two pieces are, well, we got this t out front from above, but we'll have t times the inner product of x with itself, and we'll have the inner product of x with y. It looks a little like a distribution thing. It's linearity is what it is. And a similar behavior over here. Okay. So we got roughly the same thing here as we got here, only we had an x in the first entry there and a y in the first entry in the second one. Anyhow, so that produces this. Shouldn't have any surprises with following this. What's motivated them? Sit tight. That's the exotic part, in my opinion. Okay. We can distribute here. We get a t squared inner product of x with itself. I like the sound of that because we're talking about inner product of x with itself. Here we've got a t times the inner product of x with y. Here we've got a t times the inner product of y with x. But we've got that little commutativity property in the real setting of inner products. So inner product of x with y and inner product of y with x are the same. So we've actually got 2t inner product of x with y, same. And let's see, we had an inner product of y with itself left over. So this expands out by the properties of inner product to give us this. And I want to write this for reasons to be made apparent here in a second. Let's write this as a t squared plus bt plus c. T squared term, t term, constant term. To do so, we'll need A to be the inner product of x with itself. We'll need B to be, we're including the 2 in that, twice the inner product of x with y. And we'll need C to be the inner product of y with itself. All right. So we've got a quadratic. We put no constraints on t just yet. We've got a quadratic that is greater than or equal to 0. So if you were to graph this, and we were given x and y, so A, B, and C are all determined from x and y, they're constants, but think of t as varying. So if you were to graph at squared plus bt plus c, that'd be a parabola. Opening upward parabola or opening downward parabola? Concave up, concave down. Well, the A coefficient, inner product of x with itself, that's positive, unless x is a 0 vector, in which case the result's trivial. So without loss of generality, suppose x is not the 0 vector. So A then is positive, and we've got an opening upward parabola. And this opening upward parabola is greater than or equal to 0. So think about the graph. Opening upward, concave up parabola. Where does it sit in the xy plane? Can its vertex be above the x-axis? Yeah, if its vertex is above the x-axis and it's opening upward, then all these values are above the x-axis. All these values are strictly greater than 0. What if its vertex sits on the x-axis? Then all but one of these values is above the x-axis, and the one on the x-axis is the value that corresponds to the vertex, the lowest point of that opening upward parabola. So we'd have greater than 0, and at one point we'd have equal to. Hey, could the vertex of this parabola be below the x-axis? No, then you'd have a value that's less than 0, not greater than 0. So when the vertex is below the x-axis, we got a problem. If the vertex is below the x-axis, then if you look at at squared plus bt plus c and they set it equal to 0, you get 2 distinct roots. If the vertex is below the x-axis, we'll have 2 points where this opening upward parabola intersects the x-axis. You can't have that. You have 1 when the vertex touches the x-axis. You can't have 2 places where that parabola intersects the x-axis. You can't have 2 points where this is 0. All right, well, let's set this equal to 0. Use your pal, the quadratic equations, just quadratic and t, and see what that gives us. All right, so if we were to set at squared plus bt plus c equals to 0, that'd give us, by the quadratic equation, t equals negative b plus or minus some stuff over 2a. But if we get valid real values for this square root of b squared minus 4ac thing, that's going to give us 2 different places where the parabola intersects the x-axis. And that won't work for this inequality as explained. So we need to not have 2 distinct values. We need the discriminant, remember that word, b squared minus 4ac. We need that discriminant to be either 0, in which case we'll get a 0 here in a unique solution, or negative, where we don't get any solutions for this, any real solutions. Geometrically, when b squared minus 4ac equals 0, that corresponds to that opening upward parabola sitting on the x-axis. When we get b squared minus 4ac less than 0, that means there ain't any intercepts with the x-axis. Yeah, that's because that parabola is above the x-axis for such values. And that's what we need for this inequality to be satisfied. I told you it was exotic. So what we need is b squared minus 4ac to be less than or equal to 0 for this inequality to hold. Okay, let's rearrange that. We'll take the 4ac to the other side. How about we divide both sides by 4, apparently. Rewrite the left-hand side as b over 2 squared. We need b over 2 squared less than ac. B, let's get back up to the inner product stuff. B was twice the inner product of x and y. So B over 2 is the inner product of x and y. So we get the inner product of x and y, inner product of x and y squared, is less than or equal to AC. A was the inner product of x with itself. C was the inner product of y with itself. We get that on the right-hand side. So we've got inner product of x with y squared, less than or equal to inner product of x with itself, inner product of y with itself. Let's take square roots of both sides of that inequality. Square root function is an increasing function and preserves inequalities. Square root of the quantity squared leaves us with the absolute value of the inner product of x and y. That's what we're looking for. Right-hand side, you pick up the square roots. You pick up the powers of 1/2. And there's a proof of Schwarz's inequality. A rather exotic proof, in my opinion, with this oddball little appeal to behaviors of a second-degree polynomial of a real variable. In sophomore linear algebra, we didn't give that kind of proof. I've seen this kind of proof floating around out there, so it's not uncommon. But it isn't very, well, I don't know, it's marginally geometric, I suppose, when I talk about the behavior of this parabola in terms of an inequality. But it doesn't give me much ideas about vectors. But that establishes, rigorously, Schwarz's inequality. Of course, why you want to do that? So we can prove the triangle inequality for norms. All right, formal definition of a norm. A norm on a set of vectors from Rn as a function from that set of vectors into R, actually non-negative reals, satisfying the following. If x isn't the zero vector, then the norm of x is greater than 0. And the norm of the zero vector is the zero scalar. Non-negative and mapping of the identity, they call it. Scalar A times vector x in norm equals the absolute value of scalar A times the norm of vector x for all appropriate vectors and for any scalar. Straightforward. We haven't defined norm yet for Rn, but we will here in a second. These two pieces straightforward to show. And thirdly, the norm of x plus y is less than or equal to the norm of x plus the norm of y. Your old pal triangle inequality for norms. So we're defining a norm. So a real valued function on a set of vectors that satisfies these three things is called a norm. If that set of vectors itself is a vector space, then together with the norm, we have a normed linear space, or simply norm space. I like normed linear space myself. This is the kind of verbiage we'd use in analysis. Alrighty, so that's what a norm is. We don't have it defined yet. What we've defined is Rn is a vector space, and we've defined inner products on Rn. Well, let's use that inner product to define a norm on Rn. It ain't the only norm on Rn. Euclidean norm on Rn is a familiar norm from sophomore linear algebra, defined as want to take a norm of a vector, I square its components, add them up, and take a square root, which I can accomplish with the inner product as the inner product of x with itself, square root of. Okay, it satisfies all those properties. If you don't use the zero vector, of course, that means one of those components is not 0, so the absolute value of it's greater than 0. So the norm of the whole thing, viewing the summation stuff here, is greater than 0. The norm of the zero vector is a zero vector. The behavior of scalars multiplied by vectors, straightforward. And the only thing I can think to go through on this is see where the absolute value comes from. We take A times vector x, that's A times a vector with the components, x1 through x sub n. Scalar multiplication has been performed. We'll sum the squares of the components, add them up, take a square root. All right, we'll have a common factor of a squared that we can bring out. Now let's, in a sense, distribute the square root. Square root of a squared is the absolute value of a. That's where the absolute value came from. And then the square root of the other stuff is just the norm of x. And of course, then the norm of ax equals the absolute value of a times the norm of x. How about the triangle inequality? Normally, an ambitious undertaking, but we've got Schwarz's inequality. You always prove the triangle inequality using some version of Schwarz's inequality. Okay, we got Schwarz's inequality, so off we go. We want to show triangle inequality. We want to show this. We want to show the norm of x plus y is less than or equal to the norm of x plus the norm of y. Okay. How about we take the norm of x plus y squared, which I can compute using inner products. That's the inner product of x plus y with itself. Properties of inner product, the linearity stuff. Let's just break this up as inner product of x with y, twice the inner product of x with y, and inner product of y with itself. We just did basically the same thing in that proof of the previous theorem. Properties of inner product in terms of linearity, let us do that. Hey, how big is 2 times the inner product of x with y? It's at most inner product of x with itself, square root of, inner product of y with itself, square root of. It's that value at most by Schwarz's inequality. Schwarz's inequality said the absolute value of this was less than or equal to the product of these two things here, excluding the 2. Okay, so you're not bothered by the absence of an absolute value, are you? I mean, these are real numbers. So if we've got the absolute value of the inner product of x and y bounded by this quantity down here, then we've certainly got the value x, inner product of x and y, bounded by this. Okay, so if I use then our definition of norm, here we've got the norm squared of x, here we've got the norm of x, here we've got the norm of y, here we've got the norm squared of y. That's a norm of x plus the norm of y squared. That's what you use Schwarz's inequality for, to turn this thing into a perfect square. You take square roots of both sides, triangle inequality. So there's a super quickie little proof of the triangle inequality. I like putting on comprehensive exams. Use Schwarz's inequality to prove the triangle inequality. Maybe in a setting a bit more exotic than Rn. If you're in Rn, here's how you do it. If you're in another inner product space where the inner products may be more involved, maybe it's defined in terms of integrals, doesn't matter. You use Schwarz's inequality. Awfully similar to this. The notation will vary, the argument will be exactly the same. Well, there's more norms than just the Euclidean norm on Rn. Now, I think I've mentioned this in the past. The fact that we're using a Euclidean norm, we should go back up and elaborate on this a little bit, tells us these spaces that we're dealing with, they're flat. Who gives you all this stuff with measuring distance effectively the way we're measuring distance when we use this squaring square root stuff? This squaring square root stuff, totally Pythagoras gives you that. The Pythagorean theorem is based on the parallel postulate. And what we're doing here, because we're using norms of this sort, tells you what we're doing here, everything is Euclidean. These are flat spaces, whatever that means. So all this stuff you do in linear algebra deals with these Rn spaces, and they're flat. You might look at curved spaces. But to do so, you start with these little pieces of flat spaces. Beyond our problem at this stage. We're not worried about curved spaces, but I feel compelled to point out all this Rn stuff, these are all flat spaces, not curved spaces. Why is that? Because somewhere underneath all this stuff, the parallel postulate. And the parallel postulate tells you Euclidean geometry. In other words, you're dealing with flat geometric structures. Well, here's another norm that we could put on these spaces. Let's take Rn, the LP norm, little LP. So what's the font used here? The LP norm, denoted by taking the norm symbol, putting whatever it is you put inside it there, and a little subscript of a p, where we are requiring p to be greater than or equal to 1. Otherwise, we got some problems with the triangle inequality. Take a probably graduate real analysis. We'll explore the LP spaces more, graduate real analysis too. And we'll look at LP spaces more and in a more general setting too. But if we'll define the norm of vector x from Rn, so we're still looking at Rn because that's what we're doing here. The LP norm is defined to be the sum from k equals 1 to n of the absolute value of the components to the p power pth root of. Yeah, I don't want to get into showing that's actually a norm, not in this class. There's a time and place for everything. We do this and might even touch on this in senior level analysis. If we take p equals to 2, this is the same thing we have. This is the Euclidean norm. You're likely to encounter these LP norms and LP spaces in the future. They are examples of Banach spaces. They're quite interesting if we'll allow them to be infinite dimensional, which we do. Like I said, infinity, it's got to be the realm of analysis. We deal with that in an analysis setting where we dealt with infinite dimensional normed linear spaces. Infinite dimensional normed vector spaces. Linear space, vector space, same thing. The little L they use here, in fact, is for linear. But Banach spaces are particular kinds of vector spaces with norms on them. You may have heard the term Hilbert space in your travels. A Hilbert space is a vector space with an inner product on it, preferably infinite dimensional. If these things are finite dimensional or isomorphic to Rn. You know, from the fundamental theorem of finite dimensional vector spaces, hey, you got an n-dimensional vector space with real scalars, it's isomorphic to Rn. And an additional norm you might have seen is the, sometimes it's called a sup norm, maybe it's called a max norm. We'll take vector x and define this infinity norm to be the maximum of the absolute value of the components of vector x, sometimes called max norm, which makes perfect sense if you're in finite dimensions, and these vectors have finite numbers of components. Sometimes it's called a sup norm or a supremum norm, but that would be more an infinite dimensional setting. But the claim is, anyhow, this thing is a norm as well. Gentle gives an argument that if we'll take a limit as p approaches infinity of the LP norm of a vector, then you get this max norm, this infinity norm out. And that's the reason they put the infinity symbol down there. It's a limit. I did not care much for what our textbook does on page 18 to establish this. We'll do it upright in an analysis setting and in a more general setting too. Statisticians, so I hear sometimes call this L infinity norm the Chebyshev norm. All right, so we'll look a little bit more at norms. I'll take a little break right now and we'll come back and finish up this section in one more video. I will see you there.